Leonardo Pisano, better known by his nickname Fibonacci, was the greatest European mathematician of the Middle Ages. Fibonacci played an important role in reviving ancient mathematics and made significant contributions of his own. His book Liber Abaci, or Book of the Abacus, introduced the Hindu-Arabic place value decimal system and the use of Arabic numerals into Europe. Fibonacci enunciated a sequence of numbers, the Fibonacci numbers, based on a simple arithmetic relationship. A problem in the third section in Fibonacci's book, The Liber Abaci, led to the introduction of the Fibonacci numbers and the Fibonacci sequence, for which Fibonacci is best remembered today. The problem goes as a certain man put a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from that pair in a year if it is supposed that every month each pair begets a new pair from which the second month on becomes productive? In this problem, Fibonacci wants us to assume that the rabbits always produce one male and one female offspring. The rabbits can produce once every month, and the rabbits can produce once they are 1 month old, and the rabbits never dies. Let's think in terms of how many pairs of rabbits are in the pen at the beginning of each month. Starting with one newborn pair at the beginning of the first month, these newborn are too young to reproduce, so we begin at the second month with one pair as well. It's the same pair, but they're now adults that are mature enough to mate. As a result, one new pair of rabbits is born at the end of the second month. So at the beginning of the third month, we have a total of two pairs. The original pair again mates at the beginning of that month, but the newborn pair does not. The original pair produces another pair of offspring, so at the beginning of the fourth month, we have a total of three pairs. The original pair, their newest offspring, and their first pair of offspring, which are now adults. Two pairs can now mate, and they each produce yet another new pair, giving a total of 5 pairs at the beginning of the fifth month. Now 3 pairs can mate, so after the 3 new pairs of offspring are born, our total number moves to 8 pairs. At this point, the sequence is 1, 1, 2, 3, 5, and 8. Do you see some pattern in this sequence? Well, there definitely is a pattern present. So in this pattern, each number is obtained by adding together the previous two numbers. In this case, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and 3 plus 5 is 8. You can keep going and going to find the subsequent numbers. And after the 12th month, you'll get 144 pairs. In conclusion, after a year, there will be 144 pairs of rabbits. To clearly define Fibonacci sequence, Fibonacci sequence is a series of numbers governed by some unusual arithmetic rule. The sequence is organized in a way a number can be obtained by adding the two previous numbers. This is the Fibonacci sequence. The individual numbers within this sequence are called Fibonacci numbers. These numbers were derived by adding the two previous numbers. For example, the number 21. The number 21 was derived by adding the numbers 8 and 13. The number 55 was derived by adding the numbers 21 and 34. The number 144 was derived by adding the numbers 55 and 89.
Golden ratio. It's a number that's equal to approximately 1.618. This number is now of 10, known as pi, and is expressed in writing using the symbol for the letter pi from the Greek alphabet. Pi isn't equal to precisely 1.618 since, like its famous cousin pi, pi is an irrational number, which means that its decimal digits carry on forever without repeating a pattern. How is Fibonacci sequence related to the golden ratio? As the Fibonacci numbers get bigger, the ratio between each pair of numbers get closer to 1.618. This number is called pi, or the golden ratio. The golden ratio can also be found using two quantities, like the lengths of two line segments. Two quantities have the golden ratio if their ratio is the same as the ratio of their sum to the larger of two quantities. A golden rectangle works in a similar way. A golden rectangle is a rectangle with a long side of a plus b and a short side of a. If we cut off a square section so that each side is equal to the shorter side, this is the pale blue square on the left. The piece that remains has the same ratio of side lengths as the original rectangle. This is the pink area on the right. The ratio between sides A and B is pi, or 1.618, as you can see in the equation below. We can grow this pattern by adding a larger square to the long side A plus B of a rectangle. Then we can do the same thing to the rectangle that results from the combination. You can see the pattern of squares and rectangles in this diagram. We can take the golden rectangle one step further by adding a line that forms a quarter circle in each square. This diagram shows that the lines connect to form a spiral. Each square is also labeled with a number that indicates the lengths of its sides. They are the same as the number as in the Fibonacci sequence. We call this a Fibonacci spiral.
Fibonacci numbers are found in art and nature and has been cited as a generative form describing the patterns and growth sequence, especially in nature. In art, artists use ratios of Fibonacci numbers to create pleasing rectangles in paintings and architecture, and to represent proportions of the human body. In nature, consecutive spirals of a pine cone, a pineapple, and the seeds of a sunflower head occur in the same sequence as Fibonacci numbers. The number of leaves or branches on many plants also occur in consecutive Fibonacci numbers. This could only mean that the Fibonacci numbers can be seen everywhere. Objects ranging from the shell of the nautilus on the micro level and galaxies on the macro level.